So, good morning. Welcome to the 10th session of the Pvcon 2020. This is Abdullah Buğran Karaveli speaking from the Ministry of Energy and Natural Resources. So, I will be chairing this session that's on solar energy resource and PV solar input assessment, PV power plants, and building integrated photovoltaics. So, we have 7 presentations within this session. So, each presentation has 15 minutes. For the presentation, then we have 5 minutes of question and answer session after each presentation. If the audiences have some questions to ask, please send them through the message box, then I will address these questions to the presenters. So the first speaker is Deniz Gören from Meteonorm Cyprus campus. The subject is on quality assessment of on-site solar radiation data and estimating the low voltage radiation in Meteo and CC. So the floor is yours.
Today, I will present our study about quality assessment of on-site solar and estimating global tilted irradiation in Meteo and CC. My outline starts with introduction, methodology, results, and then conclusions. So, bankable datasets are required to reduce the uncertainty of the solar PV energy projects and also to guarantee the investments of large-scale solar energy projects. Typically, TMY data is used actually for rough modeling, and also reanalysis data is used in the wind energy, for example. And satellite-based data is mostly available globally and can also be used. But the ground measured data is mostly preferred if available and if it's high quality. For the methodology, you can see the flow chart of our methodology, which we use our measured GHI and DNI data, and we do some quality assessments while constructing the GHI and then estimating the tilted irradiation, and finally we estimate the energy yield. We use MATLAB software while doing the calculations, and also we compared our data with satellite-based data, which was downloaded from the PVGIS, and it's PVGIS SERA data. In these heat maps, you can see both GHI and DNI data through the whole time period, but DNI is measured since after the second half of the year 2013. And here for the DHI, you can see some suspicious data. For example, there are missing data, time shifts, spikes, physically impossible values. Also, it may have calibration errors and even sensor failures. So we did the quality assessment actually to correct these data. First of all, some adjustments were done. Leap days were removed, and sunset and sunrise times were converted to 0 to prevent the cosine error. And also nighttime data, which is after sunset and before sunrise, were converted to 0 again. For the quality assessment of GHI, we used the physical threshold tests and also the quality envelope test. And the 10-minute data were averaged to our data. To estimate the GHI, we used the inversion of the ERPS model, which can be seen since we have the measured DNI data for the last years. And then we estimated the diffuse components from the relationship of GHI and DNI. And we used the isotropic sky diffuse model for estimating the tilted irradiation GTI. For energy yield estimation, we did it for each hour, and you can see the PV module efficiency equation and also the PV module temperature equation were used. And in these three equations, these are our parameters, which are the inputs. And these calculations were done for 1 megawatt peak solar PV power plants in Metro NCC. And you can see the details of our ground measured data and equipment details in this table. And here is our time series data of our 10-minute ambient temperature recordings. This time series date graph tells us both the GHI, the beam on horizontal surface component, and the black ones are for the extraterrestrial irradiation, which we calculated using this equation. For the gap filling, for the missing data, we used linear interpolation if it is up to 2 hours of missing data. And then we estimated the GHI using the previously mentioned ERPS model, if it is suspicious. And if both GHI and DNI is missing, which was so for only 5 days in this 7-year period, we replaced GHI and DNI with satellite-based data. So to talk about the results, we also did a replacement for the specific time periods in July in 2011. Because there was a lower than expected GHI, as can be seen in the left figure. And what we did was that we replaced it with satellite-based GHI by multiplying with a constant, which was obtained from other years of the satellite data, because we didn't have any DNI measurements in this year. For 2014 and the other remaining years, we estimated the lower than expected GHI values by using the ERPS model when it is needed. And you can see the new constructed GHI data as green on the right figure. Here is the quality envelope test results. On the left figure, you can see only the measured data for 2014. And on the right-hand side, you can see the constructed data in green. So here it gives us to compare the lower than expected GHI values. And for the boundary layers of this quality envelopes, we used the upper and lower equations, which were obtained from another study done in Cyprus. And also in these heat maps, you can compare our measured GHI and the constructed GHI data. As you can see, starting from 2014, for the last 3 years, the GHI data was corrected actually. Also for 2011, for July, you can see the change. Then we found the root mean square error of our GHI values with respect to the satellite-based GHI data. Then after constructing our GHI data, after doing the adjustments, the average RMSE was reduced from about 35% to about 18%. And If we compare the intra-annual and interannual variability of GHI, we compared both satellite and ground measured data. Here you can see for the interannual variability, satellite data gives us only 2.21%. However, our ground measured data tells us it is 5.94%. They are both low, assumed. Also, for the seasonal variability, if you look at the summer months, they have the least coefficient of variation. So we can say that the most power generation will be in summer, also spring months, and the variability of GHI is lowest in these seasons. To compare our tilted irradiation with the measured GTI in 2016, you can see both satellite measured and estimated daily total GTI values. But our measured GTI is only available after March, so it was done for 10 months, actually. And the root mean square error results gives us similar results for the hourly and daily total values. But if we look at the monthly mean values, the satellite-based GTI is almost half as the estimated GTI when compared to the measured GTI. Finally, to compare the energy yield values, here you can see for the last 4 years, and actually in the last year 2017 we have the actual energy yields value, and also we had the measured GTI value, so we can also see the comparison for the last year. However, we have the estimated GTI values for the remaining 3 years, and most information has in 2016. So if we look at this year, we see that using estimated GTI when calculating energy yields underpredicts by about 11% when compared to actual energy yield. If we use the measured GTI value, it overpredicts by about 10%. And when we use the satellite-based data, it again overpredicts by about 9%. So to conclude the whole study, we saw that the average root mean square error of GHI with respect to satellite GHI data was reduced from at about 35% to 18% after doing the quality assessment. And the root mean square error of the monthly mean estimated GTI with respect to the measured one was about 21%. However, the satellite data had an error at about 11%. Also, in the year 2016, the energy yield values tells us that using the estimated GTI can underpredict. However, the measured GTI and also the satellite GTI gave higher estimates than the actual value. Here it is important to note that the PV system losses were not included in the calculations. Also, our modeling assumptions and the equations used also have an effect on the results. But if we want to include the PV system losses when calculating the energy yields, using estimated GTI will further underestimate the actual value. So we can say that the measured GTI and satellite GTI can be closer to the actual value if we add the PV system losses also. To sum up, we should either use the quality checked ground measurements, or rather than measuring GHI and then estimating GTI, we can directly measure the GTI by using a tilted pyranometer. Or if we don't have any ground measurements available for a long time, we can use the satellite-based data, since it also gave us closer values to the actual data. Thank you for listening, and if you have any questions, I can answer.
So thank you for the presentation. Two small questions. One is regarding the tilt angle. According to my understanding, your tilt angle is 30. So was it randomly selected, or did you make some optimization then find the 30? And the second question is based on the nighttime data. In the beginning of the presentation, you have mentioned that you have converted nighttime data into zero. Were there any data there? If yes, what's the reason?
Thank you for the questions. Can you hear me?
Yeah, we can hear you well.
Okay, let me answer the first question, which is the tilt angle. In the input parameters, yes, I said it is 30 degree. It's not randomly selected because this is our actual tilt angle data. I mean, we have an installed solar PV plant in this campus. So it is not for this study is not for an hypothetical study. We have the actual measurements and the tilt angle of the PV panels are actually 30 degree tilted. For the second question, which is about the nighttime data, actually there were also either negative or positive measurements of GHI when we looked in the quality assessment. That's why we also did a correction. I mean, if it is after the sunset and before the sunrise, then all measurements should be equal to zero. That's our correction.
So thank you for the kind explanations. So the second speaker is Raymond Bavazer from the Ege University. The subject is on investigation of alternative horizontal solar radiation data source in the world. So the floor is yours.
Hello everybody. Today I am going to present to you my first conference paper titled by Investigation of Alternative Horizontal Solar Radiation Data Source in the World. My name is Raymond Omar Bawazir from Ege University, Izmir, Turkey. Introduction. Due to inexhaustible and non-bloating of renewable energy sources characteristics, these receive tangible realization by governments and societies in particular developed countries as shown in the table. The total renewable power capacity for the year 2018 reached up to 1,246 gigawatt. It is worthy to know that China, United States of America, and Germany are foregrounded of the top 6 countries for the recent 5 years. It is noteworthy that solar PV, concentrated solar power, and solar hot water have significant increase for the last 5 years as depicted in the figure. Problem statement. Even though solar energy is abundant energy and within reach, this source confronts a big challenge. It is very poor in available measured data and reliable of solar radiation data source, especially in developing countries. The number of meteorology stations on the ground are limited and unevenly distributed. They are mostly located in developed countries. These measured data does not have free access all the time, such solar GIS online application. On other hand, popular solar radiation data sources such as PVGIS, Meteonorm, and NASA Power provide different readings. These contradictions in solar radiation data source makes the choice of using one of them more difficult. Objectives of this research. The main purpose of this work is to propose a new approach or choosing a close, reliable data source for solar radiation estimation, either for country or continent. It attempts to find a close solution or to give a better suggestion to this challenge of disagreement with solar radiation data sources in the absence of measured data. Herein, three popular solar radiation data sources are considered with hybrid, NASA, PVGIS, and Meteonorm. NASA Power Data Source is free open access web for public since 1997. Recently, NASA is updated to have the prediction of worldwide energy resource, in bracket power. The power solar data is inferred by radiative transfer models from satellite readings. These is evolved to enhance upon the current renewable energy data set and to generate new data sets from new satellite systems. The Power project targets three user communities: one, renewable energy; two, sustainable buildings and agro; and the third one is agroclimatology. PVGIS data source was released since 2003. It is developed at the European Commission Joint Research Center. PVGIS is online application of free charge. It provides access to solar radiation and temperature data and others. Based on satellite data, PVGIS version 5 consists of three different solar radiations: PVGIS SARA, PVGIS CMSAF, and PVGIS NSRDB, and supported by other databases from different sources. PVGIS is also a tool for photovoltaic application. Meteonorm data source is based on meteorological database containing comprehensive climatology data for solar engineering design programs at any location. Meteonorm is commercial computer program used for passive and active PV application of solar energy production. The first release Meteonorm was since 1985. The Meteonorm software database contains more than 8,000 weather stations worldwide. Depends on user requirements. It provides free choice of using computational models, which are developed in international research programs. Here, nine statistical methods are used to compare between different solar radiation data sources. Global Performance Indicator, GPI, and ranking. Since each statistical method presents different value, this makes the final decision difficult in particular long set of data. In order to avoid such problem, the authors use a new approach called Global Performance Indicator. The flow chart here is representing how to calculate GPI. organize collected data. In this work, the entire world, including 5 continents, is considered for solar radiation data sources investigation. Australia continent is not covered in this study since it is out of the domain of PVGIS and unfound major data. Each country of the continent is investigated with 4 solar data sources: NASA Power, PVGIS SARA, Meteonorm software, and hybrid. All major data used as references were collected from the World Radiation Data Center, except for UAE, Iraq, Nigeria, Tunisia were taken from other articles. For Turkey, the major data was directly collected from Solar Energy Institute at Ege University Meteorology Station by the authors. Results and discussion. All countries of all countries of each continent have investigated by 7 solar data sources. 4 of them are hybrid. The hybrid source is based on the average of available data. The comparison among sources with respect to the measured data is implemented by statistical method. GPI and rank are used to indicate which data source is preferable for the country or continent. We start with Asia continent. In the case of Asia continent, Meteonorm is ranked as the #1, which indicates the best choice for Indonesia, Thailand, Malaysia, UAE, and India. While for Iraq, hybrid source is the best. A hybrid source of NASA and Meteonorm is the best choice to estimate solar radiation in Iraq. Africa continent. Egypt and Nigeria comes up with Meteonorm as the best choice to estimate solar radiation. Meanwhile, Algeria and Kenya have the best data source with PVGIS. In the case of Morocco, hybrid of NASA and Meteonorm is preferable for solar data source. In the case of Tunisia, NASA is preferable data source to estimate and do solar applications, as in the figure. Europe continents. For Turkey and Romania, hybrid source of NASA and PVGIS is the best choice to estimate solar radiation. For France, PVGIS, the hybrid source of PVGIS and Meteonorm, is the best choice. For Norway and Spain, Meteonorm is also preferable to be used in solar application, while in Germany, PVGIS data source is the best. North America continent. In North America, it is difficult to have common data source for all countries. Each country is different from others in terms of GPI. Because of this, we don't have common base for North America continent. South America continent. For the case of South America, the 4 studies locations, Colombia, Chile, Venezuela, and Guyana, have a single solar data source, Meteonorm, as it is depicted in the figure. At the end, estimation solar radiation on horizontal surface is always the challenge for many solar applications. This is due to the observed solar radiation readings are not usually available at the desirable locations. This work investigates the best choice of using solar radiation data source among NASA-powered PVGIS, version-based Meteonorm, and hybrid within 5 continents. Based on statistical methods and GPI results, it found that Meteonorm can be used to estimate solar radiation for Asia and South America continent. This is because of all case studies, 10 countries in both continents yielded that Meteonorm is ranked as the #1 among other choices. For Africa, Europe, and North America continents, it is difficult to have common data source for each continent. Therefore, it is suggested that each country has its own data source. For example, Turkey can use hybrid source of NASA and PVGIS rather than single data source. Based on the obtaining result of this research, enhancement of all measured data and obtaining optimal angle of solar lens will be conducted in further studies. Lastly, references. You can go through all of these. And thank you for your listening.
So thank you. Is Rayman Bazer online and together with us now? No, then the questions will be directed to him in a written form. So it's past the third presentation. We have Deniz Gören again for the presentation of P50, P90 analysis of a solar PV plant in Meteonorm using the empirical method and its comparison with my results. So floor is yours.
Today, I will present our study about P50, P90 analysis of a solar PV plant in Meteonorm using the empirical method and its comparison with TMI results. My outline is introduction, theory, methodology, results, and conclusions. So first of all, installing large-scale solar PV power plants have some risks in terms of the variability of the solar resource and financial risks. So investors and the financial institutions require the probability of exceedance values of the energy yield values, which will increase the bankability of projects and the project revenues, while it can decrease the overall uncertainty and the levelized cost of electricity. So the probability of exceedance values are basically the confidence levels for the energy yields values. For example, P50 represents the mean value, which means that in the project's lifetime, it will be met or exceeded with 50% of chance. That gives us that energy yield value. So P90 value is more conservative and it is usually required by the investors, which will says that the energy yields will be met or exceeded at 90% of the time. As you can see in this graph, this is assumed as a normal distribution, and it says the P50 and P90 values. The worst case scenarios also may require the P95, even P99 values. To explain the methodology, I have used both satellite-based data and TMI data sets. Then, using the long-term satellite-based data, which has a 12-year time period, I did the P50, P90 analysis, first using the empirical method, and then I compared the results with the normal distribution assumption. Then the results of the energy yield values, I have also used them to find the LCOE. Then in the end, doing the same calculations with the TMI datasets, I compared the results with P50 values. This study was done for a 1 megawatt peak solar PV plant in Metro NCC, and I have used the System Advisor model software. And also, I also compared the different transposition models such as isotropic, sky diffuse, HDKR, and Perez models. So the energy yield values are the first year energy yield values. They are not the lifetime average energy yield values. However, in the software, the losses are also included, such as shading, soiling, reflection, wiring, and inverter. And also to find the LCOE, a linear system degradation rate was also applied, which is 0.5% per year. And the other assumptions for the financial parameters can be seen. Generally, TMI is assumed as equal to the P50 value, but this is a poor assumption and may not give the case always. So to compare it, I used different TMI datasets from Meteonorm, also from Climate One Building website, and from PVGIS. Also, I used the satellite-based data, which I downloaded from the PVGIS website, and the time period is between 2005 and 2016. In this map, you can see PVGIS SERA dataset is suitable for Cyprus. So for the results, first let's talk about the empirical results. In this graph, you see the cumulative distribution function, which is obtained by the empirical method. So blue ones show the isotropic, red ones show HDKR model, and black one is for the Perez model. So as you can expect, the lowest estimates are obtained with the isotropic model assumption. And the vertical dashed lines are for TMI results. As you can see, for the isotropic one, P50 value was under predicted by about 7% with isotropic. Again, but by about 7% with HDKR and about by 7% for Perez model. So they all under predicted if we use the TMI datasets. To compare the empirical results with the normal distribution assumption, and also again you can see the TMI results in these graphs. First, we will look at the annual GHI graph on the left. So a general TMI result of GHI again under predicted by about 5% for P50. However, normal distribution again also under predicted the P50 value, whereas it's over predicted the P90 value by about 3%. Similar results were obtained for the energy yields, and the deviations increased compared to the GHI. So the effect of GHI and temperature was also studied. For example, it can be seen that there is a high correlation between the energy yield and annual GHI, as it's expected. However, on the left graph, you can see a negative and low correlation with the annual average daily mean temperature. So to estimate the overall uncertainty of the energy yield value, the simple rule of squares method was applied. And for data, it is 3.5%. For the transposition model, it is 2%. For the interannual variability of GHI, it is again about 2%. And these are obtained from the calculations. Other uncertainties such as dirt and soiling was assumed as 2%. And other uncertainty sources such as temperature effects are assumed as 5%. Overall, uncertainty was calculated as about 7% for the energy yields values. So to compare the results with the LCOE results also, in this graph you can see both the energy yields and LCOE results. The blue one shows the energy yields values with the error bands, and the orange ones show the LCOE values. In the middle, there are the TMI results, which can be compared with the P50 values. As on the horizontal axis, you see the exceedance probability. So as you can see, the average TMI results for the energy yields lower estimated by about 7%. As a result, the TMI over predicted the LCOE value by about 7.5%. And also, we have the actual energy yields values obtained from the PV plant station. For example, in 2016, I have put this result to the nearest value of the mean energy yields line. So it is very close to the P90 value, which can be a low solar resource year. However, if we look at the year 2017, it is even higher than the P10 value. So it gives us a comparison of the energy yields range. If we look at the interannual variability by using the satellite-based data, the coefficient of variation was used, and as I said before, the GHI variability was found as 2.21, which is assumed as low. However, as you can see, if we find the annual energy production and even the LCOE, the interannual variability increases as an effect of the temperature, GHI, and the plane of array variabilities, we can say. So to conclude, using TMI under-predicted P50 by about 5% for GHI, by about 7% for energy yields, and it's all over-predicted P50 by about 7.5% for LCOE. On the other hand, using a normal distribution assumption compared to the empirical cumulative distribution function, it underestimated the P50 energy yields by about 1%, and it overestimated P90 energy yield by about 4%. Also, the overall uncertainty of the energy yields was estimated as about 7% in these calculations. And it was found that the interannual variability of GHI is low. Thank you for listening, and I can answer any questions.
So thank you for the presentation. We have no questions in the message box. That means you have studied and explained everything clearly. So thank you. The fourth speaker is Cihan Karaman from Ege University. And the subject is the effects of photovoltaic power plant penetrations on frequency and voltage in a distribution grid. The floor is yours.
Hello, this is Cihan Karaman from Turkey, Ege University Solar Energy Institute, Izmir. Today, our topic is effects of PV power plant penetrations on frequency and voltage in a distribution grid. Our methodology starts with designing a distribution grid. We have two approaches. First of all, we have to consider the weak grid approach, and later on, we have to consider strong grid approach. And later, we created our loads and their consumptions, and PV systems also. And with the PV systems, we penetrate the PV systems into the distribution grid with changing penetration levels. And we observe the frequency and voltage results from each substation buses. In our distribution grid modeling, we have some components to design it. At the top of the grid, we can see a generator feeding the system. And between generator and transformer, there is a high voltage transmission line. And later, 3 transformers are in parallel. After the transformer, we can see the loads and PV systems connected from the substations to the distribution lines. In our strong grid approach, the layout is same with the weak grid, and we have 4 megawatt installed capacity, and we have 20 loads having changing consumptions by minutes. And strong grid, we have so low line impedances, providing 1 per unit for each substation buses. When we came to the weak grid, we have the same installed capacity and same load consumptions. But since the high line impedances, we have so low short circuit ratio and so low short circuit power and currents also. We can see the voltage level below the 0.9 per unit. As you know, demand depends on the load consumptions. If our consumptions is going to up, our demand is going to up. Especially in daylight, we have more energy, and our demand is so going up. But in midnight and midnight times, we can need less energy. In here, we selected 12 days for each month, taking the maximum consumptions from the date 2019. And our minimum consumption is in October, but maximum consumption is in July, since we need more energy in summer days and we use air conditioning devices or other equipments taking more energy. In this project, to simulate the system, we use Dixilent Power Factory software. And this software takes the calculation in clear day indexes. But we selected 2 models to calculate global irradiance and diffuse irradiance. Global irradiance is calculated by the model of Alt-Nordberg, and diffuse irradiance is calculated with the model of Luch. After that, to change the production according to weather conditions, we have to integrate the temperature and cloudy factor. And later on, we penetrate the PV systems into the grid. As you can see, PV penetration level depends on the PV installed capacity over load installed capacity. And we have synchronous generator working at 3% loop setting constantly. And we have constant line impedances for strong and weak grid separately. We penetrate the PV systems from 2% up to 75% PV penetration levels. And we observe first frequency deviations. When we look the month of July, which is having the maximum consumption, frequency deviations is getting more than the afternoon times, as you can see from the graph. This graph is belong to 75 PV penetration for strong and weak grid. For European network interconnection systems, operators taking the limits for frequency deviations, it is the 1%. If the system works in 50 Hertz, you can deviate the frequency with the generators up to 50.05 or 49.05, 49.5. This is the 1% of the frequency deviation. But in July, we didn't see any exceeds from the 1% of frequency device. And we don't need to control systems to regulate frequency. Also in this graph, we can see the power flow deviations. As you can see, 75 PV penetration, figure A, strong grid, and figure B, weak grid. In weak grid, we need more energy since the high line impedances, and loads consumes the same amount of the consumption rates. But strong grid, we don't need much energy compared to weak grid since the low line impedances, and there are low voltage drops and power losses. When we look the month of October, here is the minimum consumption, minimum demand. We saw the frequency deviation exceeds the limit 1%, but slightly. As you can see, figure A, here is the strong grid without PV, and figure B, weak grid at 75% with PV penetration. The frequency is going lower when the demand is high, but frequency going upper when the demand is low. It can be seen both of the figures. When we look up the month of the May, which is having the most PV production, figure A corresponds to strong grid without PV. Figure B, strong grid at 75 PV penetration. Figure C and D, their power flows. And since the PV production is at the top of this month, we can see the frequency deviation at 75 PV penetration is more than 1%. And in this month also, we have more frequency regulation systems to regulate the frequency for 50 Hertz. And we also take into consideration voltage results. As you can see, power flow from the top of the grid in our grid from the synchronous generator feeding the distribution grid up to bus 1 and later on bus 2. As you can see, the line impedances, resistance and inductance, there are active and reactive power losses and voltage drops. In figure B, we integrate the PV systems and power flow direction can be changed, opposite direction. And in bus 1, we can see the voltage levels going up. It is especially for weak grids, but we didn't see any voltage deviations mostly in strong grid, since there is a stability for each buses, approximately 1 per unit. And we looked the month of the July, which is having the maximum consumption. Figure A tells about without PV voltage levels. Figure B tells about 75% with PV penetration in weak grid, and figure C and D reactive power flows. Reactive power flows depends on the voltage. How? If our voltage levels is low, we need to take more reactive power flow to our buses to get the voltage is high. This is reactive power injection. It is provided by synchronous generator. Synchronous generator can inject reactive power, also can consume reactive power too. It is about under-excited or over-excited synchronous generator. But when we look the voltage levels, figure A, when our consumption is going high, our voltages is going low, and the opposite one is same. And when we look the figure B and figure D, our voltages in figure B in daylight is going up, and at that time we don't need so much reactive power from the synchronous generator. It shows that. And before getting conclusion, in this analysis, we saw that for weak grids, PV penetrations help the voltage and frequency deviation. But in strong grid, there is a stability. We don't see so much voltage deviation in strong grid, but in weak grids, due to the high line impedances and due to high voltage drop and power losses, the voltage levels deviations is more than 10%. But in strong grid, we didn't see this effect. Also, frequency deviations only depends on the power balance. If our power supply exceeds the demand, then we can see more deviations more than the 1% of the frequency. But our demand is also going low, then frequency again going up. This is important for the case of 75%. When we take into the consideration also PV low inertia and renewable energy sources, we have to take this percentage levels, because in PV systems doesn't have rotating devices to regulate the frequency instantly. They have some boxes, but in smart grids we can use it. But if we don't use it in except of the smart grid, we cannot use it. Because of that, reactive power and active power injection can be important with the high percentages PV penetrations. Thank you so much.
So thank you for the presentation. This study addressed one of the potential challenges of photovoltaics penetration into the system. So the ministry also works on these kind of challenges to find the ways to make more flexible infrastructures for the distribution grid side and for the demand side management to shape the load profile. So this is a valuable study. Thank you for the study. There's no question on the box. So let's pass to the other presentation, which will be done by Emre Demirezan from Meteonorm. The subject of the presentation is the monitoring and assessment of daily and seasonal photovoltaic heat island effect on Sekban-Demirli rural region in Kütahya, Turkey. The floor is yours.
Thank you, Dr. Karavedi. I will follow my presentation with you. Hello, my name is Emre. In this presentation, I'll explain an environmental debate which has been studied in the scientific literature for a few decades called photovoltaic heat island effect caused by solar power plants. And I'll explain our study results conducted of a project in Sekban-Demirli rural region in Kütahya, Turkey. This is my content. I introduced the heat island definition and also its subtypes and categorization. After that, I'll explain our field study and methodology to conduct this project to observe, detect photovoltaic heat islands. And after that, I'll present our graphical comparisons, results, analysis, and assess, and I'll give a brief assessment about this effect. And after that, I'll give a brief explanation for concluding remarks, and also I'll briefly explain our intention for future work. Urban heat island is a famous term, especially heat islands are known with this prefix. This term and heat island is usually defined with these prefixes, which specifies the type source of the effect, and most discussed one is this one. And urban heat islands have generally been studied according to the artificially induced air temperature rises caused by high density buildings like here. Also low density green spaces, lack of tree spawns, vehicle traffic, roads, greenhouse gas emissions of metropolitan areas. The high absorbance and reflectance of incoming solar radiation on the urban fabric during day hours are followed by the high thermal emittance, I mean long wave infrared radiation of extra heat during the night times. Because of this, daily, also plus seasonally, cycles can be detectable. Heat island cycles can be detectable. This table shows the basic features of the main urban heat island formations as atmospheric and surface, this table here. Here it's essential to note that the observations for atmospheric Earth urban heat islands are made for canopy layer and also boundary layers. And also some identification methods. You can see some mobile devices or vehicles like satellites, aircrafts, or ground-mounted versions. We use also these versions for our study, like fixed weather monitoring stations. And also automobiles, aircrafts, as I said, SODARs, sonic detection tools, and also balloons, tethered balloons, and also some weather station-mounted automobiles can be used. And surface urban heat islands is linked to the also surface temperature change, and they can be detectable via the satellite images. And these are the categorization and measurement methods you can see here. Again, fixed weather stations, aircrafts, and also their types, a thermal image also example here. These measurement methods also can be grouped under these titles and instrument types, measuring instrument types. From urban fabric to solar module arrays. What is the cause of photovoltaic heat island effect? Actually, solar modules, because they are also have heat release ways, heat loss types from their surface, and these also losses are connected, depends on three physical processes as radiation, convection, and also conduction. These module also these modules and their packing density, solar cell density, efficiencies, electrical operating points, module heat capacity, these all physical processes may affect their heat loss. And when you also install these arrays across the big, large, also uncultivated areas, you can also observe these photovoltaic heat island effects because of their huge amount of heat release to the overlying atmosphere. These are some examples you can see, for example, from Turkey and India. Karapınar Solar Power Plant and also Kurnol Solar Park. You can see these buildings here, and when you consider the also covered area of these PV modules, you can also understand the effects intensity because of these also big coverage along the natural land surface type. When we come to our project in Sekban-Demirel region, please let me first describe also some geographical features. Sekban-Demirel is a rural settlement area and 16 kilometers away from the Tavşanlı in Turkey, Kütahya, Turkey. And a power plant was constructed in 2017. You can see its plant field and capacity with these solar PV modules having the conversion efficiencies here, and also a tilt angle with 20 degrees. And also it has a village here, a neighboring village there. These are our weather stations, also located along the Sekban-Demirel region and power plant fields. And we have been collecting the 22-month data between November 2018 and August 2020. These are 10-minute averages or hourly averages. And we can also collect this data: air temperature, incoming solar radiation, wind speed direction, and PV power plants power output. We can monitor this data, and these are the main indicators to observe the photovoltaic heat island effect. And these are the supporting data. We can also collect this data, and if required, we can use to also improve the study with this data. Segment-Emirates region, when again we look at these stations and we when look at their monitoring interfaces from the internet, from the websites, from the two monitoring websites. The first one is the PlantMat and the second one is the Sunny portal. These are agricultural and meteorological data monitoring systems for the monitoring these weather measurements. And also you can visualize the power output values from Sunny portal via this Sunny portal web interface. This is the outside of the station, and these are the stations inside the power plant. And when we look at our analysis, first one is the error analysis, because the sensor accuracy of weather measurements and the confidence intervals calculated from the error analysis of each weather parameters, cumulative data, are important because if the confidence level is smaller than the sensor accuracy or accuracy, this contributes to the usability of the relevant parameter measurements as reliable data. We can say, yes, it's reliable for this, for example, parameter for air temperature or for wind speed. Because, you know, the weather stations sometimes fail to send the field data due to some technical problems. And we consider them as null values, empty values. And then when we look at these confidence, the relation between the confidence interval and sensor accuracy, you can see they are almost smaller, generally smaller here. Only the module temperature is equals to the sensor accuracy. But again, we can say this condition. We can say we also ensure the condition that all these weather parameters, they can be their data is reliable for our study, for our analysis. And how we compare this weather station data? First, we use some statistical methods. One-way analysis of variance, the first method, shows if there are statistically significant differences between the means of 3 or more independent groups. Here, the independent groups are weather stations. You can see here, and their data counts, and these are the statistical findings from their statistical analysis. And we also, according to the ANOVA results, if the air temperature measurements of weather stations differ significantly from each other, this is the first strong inference indicating the meaningful temperature differences and possible heat island formations on the location of the concerned weather station. The question is, which weather station records these formations? We need to find it. You can see this is the first condition we ensure. And the second one, Turkey test, following these ANOVA results, Turkey test shows which of the weather stations differ from each other, which is the possible source, is the possible source for these heat island formations. And when we use this formula from this table, and when we compare the averages, because this test, named Turkey test, shows which of these weather stations differ from each other. It's important to use this formula to find which of the weather stations differ from each other, and if the differences, absolute values between the averages are bigger than the HSD value, the air temperature measurements of those two weather stations, for example, those two or those two, are bigger than the HSD value. If they are bigger, like here, for example, HSD value is here, and only these two is bigger than this value, we can say these are significantly different from each other, but this is not. So we can say the center of PVP field, because this station is located in the center of the PP field, power plant field, we can say a possible heat source can be here, might be here for photovoltaic heat island effect. And also we use some correlation results for the analyze for the understand this effect, because correlation is important to understand the changing of the indicators of photovoltaic heat island effect. To support again this our inference in terms of linear relationship strength between the air temperature differences, a hourly average power output and hourly average module temperature correlation coefficients were calculated for the day and night times between between the two 22-month data. Here, delta T is introduced as the primary indicator of photovoltaic heat island formation because this is the center field, and this is for the outside of the outside the plant field, and the temperature difference is important to indicate, observe the photovoltaic heat island. Because photovoltaic power plant solar modules release heat towards the overlying atmosphere while producing electricity, the plant's fundamental parameters P and module temperature and power output should be correlated to this value. So we also calculate these whole values. You can see during the daytimes the linear relationship between these, for example, module and indicator, module temperature and photovoltaic heat island formation indicator. It tends to be stronger in from the autumn to winter, and it weakens towards the summer, and again strengths towards the winter, and finally gets weaker, like here. It's a stable also change. But for the night times, an inverse relationship we can also observe from here, and no nighttime column here, because no production during the night times from the power plant. And these are our graphical comparisons among all the 22-month data collected. Delta T percentages correspond to the distribution of delta T values bigger than 1 centigrade or smaller than -1 centigrade, you can see. Also module temperature curve and ambient temperature curve here. It's a stable also change, you can see. And these are the most observable photovoltaic heat island formations here. For the night times, less observable, but again, an inverse photovoltaic heat island effect occurs. Because the TM module curve always shows a trend line in the up. Here, the module line also shows a trend line upward on the upper position, but not very distinctly. We can't see a significant difference also here. But again, we also find some inverse temperature differences. But this time, and because of a negatives and smaller photovoltaic heat island effect, we can conclude that the center of the PVP field is colder during the night times, and because of an inverse photovoltaic heat island effect. And this is the monthly maximum ambient air temperature daytimes. You can see always weather station weather station 3 always shows the bigger also differences. The maximum temperatures also always is recorded by weather station 3, and these are very close, these stations, but the center again in the upper position, on the upper position. For the minimum night times, as we said, a less and inverse photovoltaic heat island effect condition can be seen on this in this graph. Very also especially here. Also, you can see not a significant difference, but here and here, again, during the winter times, a less and inverse photovoltaic heat island formations for the nighttime temperatures, minimum temperatures, can be observable from here. These are some examples from segment emirli. We choose two days. One of them is from November 2019 and the other for August. This is an inverse photovoltaic heat island effect, and this is a positive. This is negative, and this is a positive photovoltaic heat island effect for the segment emirli, and it's an illustration. And local winds, last but not least, we utilize this average wind speed data from the weather station measurements, and we also depicted this. We also formed this chart, these wind rows, and you can see these wind rows. These winds show that these graphs show that the prevailing winds over the photovoltaic power plant field blow from the northeast between the speed intervals as follows here, according to the Beaufort scale. This is also north direction of segment emirli, and wind comes from here to the modules, and we can ask if they affect the reduction of heat island or not. We can check it here. Delta T results in this graph associated with the wind direction below, and also the hourly average wind speeds on the right. I will show this table also, but first let me introduce this table. To understand if these prevailing winds interact with the power plant's south-facing modules and alter the daytime positive photovoltaic heat island trend. This figure gives the daytime results, delta T results associated with the daytime wind direction data. In the figure, the photovoltaic heat islands are apparent with more data points between these degrees, and you can see 45 degree, the prominent also prevailing wind direction degree is here, again with many data points. So we concluded that they are not convenient. They are not. They can't reduce to photovoltaic heat island effects because of their direction and their entrance to the field center. And this table also can be seen from these also correlation results again, and wind speed, and also the indicator of photovoltaic heat island effect. Generally very low correlations you can see for the whole months, and because of this condition we can conclude that local prevailing winds is not convenient for photovoltaic heat island reduction. And as a conclusion, when we come to our conclusion, concluding remarks and our future work title, apart from the various advantages of rapidly increasing photovoltaic heat island installations, they may bring some environmental side effects like this photovoltaic heat island effect. We also detect these differences, a positive heat island effect during the daytimes and a negative heat island effect during the night times in segment emirli, and also winds, as we said on the previous slide, is not capable, is not being capable of reducing heat island by natural convective cooling of its natural, because wind has this feature, this property, but because of the orientation of the PV modules, the wind can't affect the photovoltaic heat island effect reduction. And also because of this northeast blowing direction. And as for the last words, we also intend to use a microclimate urban heat island simulation software called EnviMet for our future work, for our next work. This software provides a detailed simulation work by considering the weather parameters like, again, air temperature, relative humidity, and like this. And also solar radiation albedo analysis can be conducted in this also software for some geographical locations. And after that, we will able to integrate, add these extra analyses into our current findings, current analyses, current comparisons and methodology, and develop our content of our study. We intend this. Last but not least, we would like to thank Mr. Oğuz Aydın and Mr. Tolga Eryashar for their technical assistance, and Mr. Hakan Akınoğlu for his contribution to the study's illustrations. Thank you for your attention.
So, thank you for the kind presentation. Just out of curiosity, I have two small questions. One is regarding the threshold. Is there any threshold for the installed power? That means if you are below that threshold, then the heat island effect is negligible, and over it, it has a reasonable heat island effect that we take into account. I mean, do you just take into account heat island effect in the Karapınar region and that much scale photovoltaics, or even you have 1 megawatt, it has a reasonable heat island effect? Can you say this? And the second question, just on the negative heat island effect at the night time. What's the main reason for that?
Thank you for these two nice questions, Dr. Karaveli. For your first question, actually, we are working on a power plant having the installed capacity 2.5 megawatts. When we consider the whole capacity of Karapınar as 1 gigawatt, actually, I think the effect can be more observable. Also, Konya has a flat geographical topography region. So if we conclude these results for Sekban-Demirli region with a smaller installed capacity, I think we can, with more weather stations, I think we can detect different also trend lines for photovoltaic heat island formations, observations. But especially in this type of studies, the topographical features of the region, of the uncultivated areas, like again Karapınar or like Sekban-Demirli, it's important to also simulate. It's important to model these structure into a software. Maybe after we simulate the results on ENVIMAT, the last slide you'll see also, you can again check this software from their website. When you simulate these results for these small, respectively small power plant in ENVIMAT, I think again a simulation for bigger power plants like Kurnol in India, or like the mega gigawatt scale power plants like in China or United States. I think you can simulate their also scenarios without, for example, mounting, without also installing a power weather station there. But the weather station data also support the study. So as far as we do, we can take these measurements. Maybe Karapınar also can support this type of a project for us for the future studies. For your second question, I think for the night times you ask for this, isn't it? Can I again listen your question, the second question?
Yeah. When we think about the effect, we always think that it has positive effect on temperature, but in the presentation there was a negative heat island effect at night times. I asked the reason why there is a negative effect.
Actually, interesting, when we look at the recent studies and literature studies, some inverse effects also have been found within their research projects. But generally they say, especially for heat islands, let me please first say for urban heat islands, generally urban heat islands are more distinct during the night times because of the fast cooling from the artificial urban fabric, urban surfaces like pavements, vehicle, for example, rooftops of the buildings. A bigger also heat loss to the thermal heat loss to the overlying atmosphere also occurs during the night times. But for the photovoltaic panels, because of their thermal inertia and also some heat capacity issues, now we are also working with our colleagues about it. An interesting and inverse effect, but less observable effect occurs. And actually, we are also intending to understand these past heat loss because, for example, after 11 p.m. or 10 p.m., directly you can see this inverse effect in opposite of an urban heat island formation. We are trying to understand this effect by relating this issue to the panel structure and to the thermal also processes within the physical structure of the panel. Maybe MVMET and also some physical new formulas can improve the study with these with our new findings. I think at the third stage we will also develop the study with these new also findings related to your question, for example.
So thank you for the detailed explanations. The next speaker, Ahadullah Hazami from East Mediterranean University. Then the subject is on energy efficient building form and building integrated photovoltaic performance. The floor is yours. So Mr. Azami, can you hear us?
Let me to share my file. I have a technical problem to share my file. Let me to do it. How can I share?
Did you try to share the screen right on the below top?
I want to share my files through my mobile, but and laptop also. But I have a laptop. Okay, I found it. Just a moment. Yes. Can you see my screen or not?
Yeah, we can see it now.
Okay, thank you. And also, Please wait only just a moment. Okay, dear madam and sir, dear participants. Oh, just a moment. I should. Yes, my presentation is about energy efficient building form and Bipv performance. I will start my presentation with abstract introduction, methodology, analysis, and conclusion. So there's an echo. I don't know how to solve it, but excuse me, can you turn up my voice through the laptop or not? Because I have echo here. Hello? Okay, I should start. At the first, because of the building form, and as I know, and you know, building form play an important role in energy efficiency and solar energy gain as well. So energy efficient building design is dependent on the contextual principles and local climate conditions of the specific site. So building envelope plays a dual function of energy transition and creation through its surfaces. Especially the compactness, which is the area to the volume of the building form, is very important because of energy demand and energy loss as well. But here we have two concepts should be analyzed: passive house and active house concept. What is passive house? Passive house is about low energy building with minimize the compactness and low energy loss. On the other side, active house is about optimum compactness with high energy produce and production. But from the other hand, we have building integrated photovoltaic concept, which is about PV integration into the building envelope, especially on the roof and facades. And finally, I will continue this part with energy balance between energy creation and energy loss. Building integrated photovoltaics is about PV integration into the different building types with different methods. You can see here, but Bipv design can be analyzed as applied seamlessly, or maybe added to the design as an additional element, or maybe added to the architectural image, and also added to the used to determine the architectural image. And finally, used to explore new architectural concepts, because it will give added value to the architectural forms and also different form types. Various options of integrating photovoltaics into the construction. As we mentioned before, about addition, substitution, and integration, and all of them have different configuration. I mean about PV configuration and integrated to the buildings, from standoff, integral, and standoff on the pitch roof. You see flat roof and pitch roof. We have three available surfaces for integration: roof, facade, and sunshade. But the best place is roof. But in populated cities like Ankara, Istanbul, and populated cities and mega cities, facade will be better. Why? Because we have more facade surface area than roof area. So we should optimize and find the available and optimum surface area on the envelope. Finally, in this part, Bipv system interface with utility grid, but how? Both the building owner and utility benefit with grid charge PV on-site production of electricity, reduce owner energy cost, and explore solar electricity helps support the utility grid. So BIPV has many, many advantages. But power production of BIPV is dependent on solar radiation, solar altitude, I mean about the tilt of the PV surfaces. Also solar azimuth and temperature. And finally, shading or shadow dirt accumulation cell efficiency. There are many ways to determination of the PV potential by calculations through softwares and other calculation methods. But one of them is very simple, is about sunnet calculation, production of solar electricity is about available area per capita, multiplied by utilization factor, solar yield, population size, solar radiation, and finally global conversion efficiency. Okay, now it's a time to analyze the climate of Ankara. Yeah, just a moment. To 2,000 kilowatt hour per square meter, but in Ankara, it's about according to the color here, we have 1,550 kilowatt hour per square meter. Especially here, photovoltaic power potential is about, according to the color here, is about 4.2 kilowatt hour per kilowatt power. Other analysis about climate of Ankara. It's about a cold, dry climate according to the temperature you see here, especially in January, we have a lowest temperature here. So we will have a high loss of energy, especially in winter, during the winter months. Global horizon radiation, you may see here the maximum is about 862 watt-hour per square meter. Also, global horizon radiation as a graph, very simple. You can see here the maximum occurs in May until August. Direct normal radiation, maximum is in July, but other months we have a little bit. But in some months, like January, we have the minimum one. For theta surface radiation, we have the maximum. You can compare this one with this one. And also 3D graphic about direct normal. Here about theta surfaces. You may find a better one. And this is about the psychrometric chart of the Ankara. We may have better strategies, as you see, best of design strategies here. So we may have a better function role for solar energy, especially as passive and also active radiation. Okay. This paper has a very simple methodology. Firstly, different form types are configured and analyzed according to their forms about their energy creation and energy losses to find energy balance according to the active house concept. As we mentioned before, that active house is better than passive house because it will give us more potential for available area for PV integration. So by this simple methodology, we may have energy efficient heating form to have a better BIPV performance. Yes, these are different form types. You may see separated form types, cubic form, 4 cubic forms. They might be configured separately or as vertically, horizontally, 2 by 2 as a big cubic, vertical and horizontal, and also 2 separated, 2 by 2. So we are going to analyze these 6 form types. This is analysis. As I mentioned before, compactness is about surface area, total surface area. You see 6 surface area for each form. So if you divide total surface area to the volume area, you will have compactness. It will be 2. For the second form, C would be 1.67. For C form, C would be 1.5. But for the D form, it will be 1.5, for D form 1.3, and for F form 1.6. Okay, what should we do? We have 2 analyses here. One of them is about potential energy creation through the building envelope. Here, this is the maximum for what? For roof. This is for roof. For south wall, for east-west wall, and also for north wall and flue. You know, we have no solar radiation in the flue because it's in the bottom. So if you check the surfaces, you will have diagram, very simple diagram, but effective diagram like here. For the second form, the first part is as the same, but in the third part, I mean about low yield east-west wall. We have minimized for ratio less than the previous 8.1 type. Here we have, like before, but we have two ratios less than the previous one, and also in this in the vertical form we have only high yield. It means that roof, we have only one roof surface area as a model. But here for the east-west wall we have we are in a better situation. For the floor we have minimum. For this E-form type, we have the best situation, also surface area available for PV integration into the roof. 4, you see 1, 2, 3, 4. But here, 2 parts, two part or 2 unit for this one. Okay, for this energy creation, we can compare all of them together. Which is better? This one because of the roof, and also about the facade because south wall is the better. So this one, and also yes, these are. From the other hand, we have heating loss or energy loss, or maybe we can say that as a heating demand. We should increase energy creation by PV utilization as integration into the building envelope, and also reduce the heating demand or heating loss through the building envelope, exterior surfaces, exposed surface area. Here, like the previous one, like energy creation, roof has the most energy loss, 4 unit, 4 unit. We can compare these together. For this part, they are the same. See, they are the same. The same. But here we have another issue, or here we have another issue, because we have this part, medium loss, I mean east-west wall, this part, and the low loss here. But here high loss because of the roof. You see, we have the best situation here, best option for PV integration. But from the other hand, we may lose energy through the roof area, roof envelope area. Also, you may compare this one. It's very bad because of the high energy loss from the east-west wall. also here, and finally from this part, it's bad comparing to the previous one. Why? Because of a medium and high energy loss, also high energy demand through the S wall and also salt wall and proof. Okay, as we mentioned before, the minimum concept, the minimum compactness means that we have less surface area outside. So which one is better? The minimum one here is this one and this one, E form and F form. But based on the comparison between energy creation and energy demand, you'll find that this form would be better, not less, it is in between these values. The maximum is 2, the minimum is 1.3, 1.5, but we have 1.5 here. But this has, this form has a small surface area in the roof, at the rooftop. So this would be better. This is a very simple calculation. Before more complex calculation, to find the best form type to have more energy creation while reducing heating demand. So whose overall balance will be assigned for form C. Based on our analysis, optimized roof size orientation and also building form, we can appreciate ratio compactness for the selected form types, resulting in better Bipv performance for energy creation. Also, due to the seasonal distribution, Bipv performance of facade is higher than flat roof in winter and transition months. I should mention that also the compactness of building is an important parameter in optimizing their energy losses. The smaller the area of the envelope, I mean A, surface area, related to the volume B, the better loss performance. Active house building, however, generates energy from the facades, therefore minimizing the envelope area alone is not enough to fulfill the design's goals, as we see here. A medium degree of compactness, as we mentioned here, produce the best result. Optimum compactness with optimum energy creation and optimum energy loss. So, two equal compact buildings can have different potential here. Different potential for creating energy depending on whether they have been optimized in orientation and building form. Thank you very much, and thanks for your attention.
So thank you for the presentation. So in these days, we have a very hot agenda on the nearly zero energy buildings. So integrating photovoltaics on the facades with the isolation structures, the solution will be very perfectible. So this study addresses these issues very well. So thank you for the presentation. There is no question on the box list. So let me pass to the last presentation of the session. That's from Raymond Bavazir from the University. The subject is designing of an on-grid and off-grid photovoltaic system with battery. The floor is yours. Could you please share the last presentation?
Hello, everybody. Today, I'm going to present to you my conference paper titled by Designing of on-grid and off-grid PV system with battery. My name is Raymond Omar Bawazir. I am from Ege University, Izmir, Turkey. Introduction. In this study, the PV power system is designed which is able to operate both on-grid and off-grid. The main components of this system are PV panels, power electronic circuits, and batteries. This system is producing electricity without polluting the environment, depending on the grid to the minimum level. If the grid power cut, loads can continue to operate and payback period is shorter than other PV systems due to the different operation modes. This study is conducted in Untitled University in Diyarbakir, Turkey. Materials and methods. In this study, hybrid PV power system is developed. This system can either describe as off-grid with utility backup power or grid-side solar with extra battery storage. The block diagram of this system is shown in below figure. The power of PV system was selected as 5 kilowatt. This PV power system has different operating characteristics at 4 different time periods of a day. While determining this time period, energy consumption values and different charges in different time periods for grid electricity are taken into account as well as sunshine duration. According to this, the operating style of this system has been constructed as in next slide. Morning. This time period covers between 8 a.m. to 12 a.m. The produced energy by the panels provide energy requirements of the load and charges the battery in this period. The current way is shown in the figure with red line. Evening. This period covers between the sunset to 24 p.m. The grid electricity cost is most expensive and the load energy requirements are highest in this period in Turkey. After sunset, the system automatically disconnects from the grid and the energy needs of loads are met by batteries. The current way is shown in the figure with red line for this period. 9. This period covers between 24 p.m. to 8 a.m. The grid electricity cost is cheapest and load energy requirements are lowest in this period. If the batteries are not fully discharged, the energy needs of the loads will meet from the batteries. However, if the batteries are fully discharged, the energy needs of the loads will meet from the grid. So the system automatically disconnects from the batteries. Energy consumption of loads. The table shows that the type of loads and the number of each load are associated with power and operating time. In this slide, we have equations that are used to calculate the energy consumption of loads. In this slide, we also have equations that are used to determine the battery capacity. Forecasting of energy production of PV panel. The system power is 5 kilowatt. The PV panels have 15-degree tilt angle and 0-degree azimuth angle. This system was analyzed in PV system program. Average monthly irradiation and temperature values for Diyarbakir are shown in the table. In this figure, it shows the amount of energy produced by this system monthly and annual. The annual energy production is approximately 7,600 kilowatt hour. This hybrid PV system needs of 2 kilowatt hour energy for autonomy period. This means large a large part of energy will transfer to the grid almost every day in a year. The comparison of needed energy during the autonomy period and produced energy from PV panels are shown in the figure. Annual needed energy during the autonomy period is 730 kilowatt hour. However, the produced energy by PV system is 1,500 kilowatt hours. So the produced energy by PV panels is more than 50% of the required energy during the autonomy period. Control unit. The system needed a control unit to work efficiently. When we examine today's on-grid applications, we will see that the PV systems that are used only day long, if it is necessary, the energy takes from grid during night. But developed systems take needed energy from grid, batteries, or PV panels. The control unit of the system measures the consumption of loads, the charge level of the batteries, and grid constantly. So the batteries are being charged only for few hours in the morning, and they are only being discharged in the evening peak hours. That is to say, the batteries are not being charged and discharged constantly as in conventional systems. This operation style reduces the battery life. The control unit has 4 inputs and 3 outputs. The inputs are PV panels, batteries, grid, and loads. The outputs are A, B, and C switches. The inputs and outputs of control units are shown in the figure. Next slide. The fuzzy logic is used in the control unit, so it is possible to provide a more successful management system according to the classical control units. Because of energy consumption of loads, charge level of batteries, and the amount of energy by PV panels are perceived as either there or not in the classical control unit. However, the values such as low, medium can be detected in fuzzy logic. This table shows the rules of control unit, different scenarios, and results. In this study, different scenarios have been determined to analyze the operation of the system according to produce and consume energy in different periods of day. In accordance with these purpose, the charging time of battery, the amount of energy to be transferred to the grid, and the amount of the energy that is requested from the grid are determined. Day period. The produced energy by PV panel varies according to the season, temperature, and radiation. In this study, December, in which the minimum energy produced takes place, and June, in which the maximum energy production takes place, are considered. The average daily energy production is 10.80 kilowatt hour per day in December. The amount of energy production before 12 a.m. and after 12 has nearly same value, especially in the sunny day in winter. So the amount of energy is 5.40 kilowatt hour before 12 o'clock in winter. Coming table shows the power of loads and their operating time. This table shows the power of loads and operating time in the morning period. Here are some equations that used for our study. You can go through. It is seen that batteries can get fully charged until 1 p.m. in December. The produced 5 kilowatt hour energy after 1 p.m. will transfer to the grid. This means the amount of energy that can be transferred to the grid is 150 kilowatt hour per month. The average daily energy production is 10.80 kilowatt hour per day in June. The amount of energy production before 1 p.m. and after 1 p.m. has nearly same value, especially in June. So the amount of energy is 5.40 kilowatt hour before 12 a.m. in winter. The previous table showed the power of loads and their operating time. The energy, which is 16 kilowatt hour, can transfer to the grid after 12 a.m. in this period. This means the amount of energy that can be transferred to the grid is 750 kilowatt hour for month in summer. The annual average daily energy production is found as 20.84 kilowatt hour per day. So the energy, which is 5,475 kilowatt hour, can be transferred to the grid. Evening period. There is no energy production in this period. It is aimed to meet the energy needs of loads from the batteries until 24 o'clock, and if it is necessary, needed energy will meet from grid until morning. The power of loads which will operate until 24 and operating time are shown in this table. Here's some equations that are used also in our calculation. You can go through. The maximum power is determined as 415 watt, which is consumed at the same time by the loads in the evening period. The discharge time of batteries is calculated according to 3 different loads power. The table next slide shows the discharge time of batteries in the evening period. It is seen that the battery's capacity will finish at 21 o'clock 30 minutes according to the worst scenario, but according to the best scenario, the capacity of batteries is sufficient during night. Also, the capacity of batteries is enough until 24 o'clock. Then, if it is necessary, the need of load will need from the grid until morning according to average scenario. This table shows the discharge time of batteries in the evening. At the end, this hybrid PV system is designed to operate both on-grid and off-grid. The energy production amount of this PV system is determined by using PV system program. The proposed system is approved. The installation in Diyarbakir. The tilt angle and azimuth angle is accepted as 15 and 0 degree respectively. As a result of the analysis, this 5 kilowatt PV system has potential to annually produce 7,600 kilowatt hour. In this system, lighting, computer, refrigerator, and TV, which are the most used devices, are preferred as load. When calculating daily energy needs of load, not only devices power and the operating time, but also the losses are considered. The daily energy consumption of loads are calculated 1,993 watt hour. This value shows the energy consumption of load during autonomy period. The capacity of batteries are calculated 4,270 ampere hour, considering the cloudy day and the discharge rate of battery. So 8 batteries, which are 55 ampere hour, were used in this study. A control unit is as designed in according with the purpose of the system to operate it both on grid and off grid. The fuzzy logic control is used in the control unit. The control unit has 4 inputs, which are load, the charge level of batteries, grid, and the energy production value of BP panel, while three output, which are ABC switches. The control unit is tested using the MATLAB program. Here the references the listeners can go through. They are 14 references provided. Thank you for your listening.
So thank you. Now we have reached the end of the session. Thank you for your participation and have a nice day and have a nice lunch.